Random forest is an idea very similar to bagging, but it uses an additional trick in the aggregation. So with random forest, we're pretty much doing the same thing as in here, but we get these kind of bootstrap samples. But when we are growing these trees, we have some restriction. The restriction is that when we get this bootstrap sample 1, bootstrap sample 2, all the way to bootstrap sample capital B, but then in here, when we want to consider a split for growing a tree like this, we don't make all the predictors available to the model. So this is a bit counterintuitive because predictors are like information, they are useful. So why we are not providing them to the model? So there are in general P predictors. There are P predictors, but we only consider a small subset of them. So when we are growing a tree on a bootstrap sample, instead of P predictors to choose from for a split, we make only M predictors available. This is some random selection out of the P predictors. A random selection of M predictors is available for the trees. So this is the data set. This is some bootstrap sample. We are growing a tree here. For the first split, we're not searching the whole space of possibilities for which variable to split on. We only search within a restricted space of M predictors. And M is much smaller than P. Sometimes it's common to use square root of P. So this is counterintuitive because we're restricting this tree, but actually this trick is going to give us trees that are decorrelated. And as they are decorrelated, the reduction in variance that we would have from aggregating those decorrelated trees would even be smaller than the case of bagging. That's why random forest is just has some additional advantage over bagging. Bagging is bootstrap aggregation. Random forest is also bootstrap aggregation plus decorrelation of the trees by searching a smaller space. So this is some sort of magical thing because we're making this process easier, and at the same time we get a better result. Something that doesn't happen often in machine learning. Here we're making the search easier by only searching between M predictors for a split, where M is, for example, square root of P. So most of the predictors are unavailable. So then out of those M predictors, we select one of them and split. Now, then for this potential split, we're going to get another random selection of M predictors, make it available to the tree to choose from, and the other P minus M predictors are unavailable here. There will be some split. Again, for this split, we have a fresh selection of M predictors. So we're doing this random selection again and again. Maybe that's why it's called random forest, because we have these random selections of M predictors for each split. So that's how we're going to end up with a number of trees. And the rest is similar as bagging. So these trees are decorrelated trees. Their correlation is relatively smaller than the correlation of the trees or correlation of the predictions from those trees with bagging. And whenever we have average of decorrelated variables, the reduction in variance will be even more substantial. It is as if I think of it as the average of the viewpoint of two people with really opposite views. The reduction in the eventual viewpoint will be more when they are from let's say political left and political right. But if you have two different individuals, both of them left, the reduction in the average in the variance of the average will be smaller. So we have decorrelated trees, and then in terms of performance, random forest may end up here. For some holdout test data, and we can also get out of bag estimate. So it just has some improvements over bagging. And this improvement is because we decorrelate the trees. So there's really no downside to this when we want to choose between these two ideas. I think it's just natural to go with random forest compared to bagging. Bagging is an idea maybe from 30 years ago. Random forest, I think it's like from 20 years ago. And it's just, it is some sort of, special way of doing bagging where we decorrelate these trees. All right, any questions? No? All right, random forests seem to be very, very simple, I guess. Well, I mean, for me, there's another reason to like random forest. The initial matches with my last name. So as someone who's literally Aref, I like random forests. So, any other questions? So, yeah. So the last type of advanced tree-based models are boosting, and boosting is kind of a separate thing from bagging and random forest. With boosting, the idea is that we're again aggregating trees, but we are aggregating them in sort of a sequential way. So the trees we had in bagging and random forest, they were independent of each other in a way. They were at least trained independently. But with boosting, we have a sequential process. So with boosting, we have this model, let's say f hat, and we have some residual, let's say r I. So it's a sequential process. In the first step of the process, we're going to set the residual to be equal to the response. So I'm explaining boosting in the context of regression because it's just simpler to think of what's happening with regression compared to classification. For classification, it's same thing, but the story is not as intuitive. So we have some residual, which is what remains to be predicted, and at the beginning of the process, everything remains to be predicted. And then in step 2, we're going to fit a tree to, well, actually, we have the bootstrap samples. So this step 2 is kind of a for loop. So we have those bootstrap samples, and we start with the first bootstrap sample. For the first bootstrap sample, we're going to fit a tree. We fit a tree to this data set, to X, which are all the predictors, and Ri, which is the remaining response. This is like some tree, right? We have it, it's a tree like this. And typically with boosting, these trees are really simple trees because we want to learn slowly. So boosting is the idea of slow learning. So we just fit a small tree, a stump, which would be just one split with 2 terminal nodes, or it can be maybe a tree with 2 splits. So d equal to 1 or 2 is kind of normal for boosting. So as this model is simple, it's not going to really, it's going to be underfit just by itself. But it's okay because this is not the end of story. Then we're going to shrink the prediction of this. So let's say the prediction of this is f hat b. Then here, our main model, which is some f hat, is going to be what it was, which was nothing at the beginning. And then we shrink this by some value like 1% and multiply it to prediction from this underfit tree. That's why at this point, our model is just some small tree times 0.01. Then we update the residual. Now our I is going to be what it was minus lambda times f hat of b. So we're kind of sequentially attacking the residual. Residual is the response at the beginning, and then we kind of take this part from it, predict this much of it, and then residual will get smaller. Yeah, and then when we go over all the bootstrap samples, we're going to have a model, which is our final model. At the end is going to be sum of over b. It will be sum of lambda times f hat of b from 1 to capital B. Yeah, so this is the process. Yeah. So boosting has 3 hyperparameters. Capital B is a hyperparameter, lambda is a hyperparameter, and also D is a hyperparameter. So we need to find these values, by cross-validation. Some of them are not that important. For example, capital B, it's just a number of bootstrap samples. Lambda is very important. So for this, we do cross-validation. D, as I said, is usually 1 or 2. We just, try 1 and cross-validate this, and try 2 and cross-validate this, and then try one of those two options. There was a question.
Isn't your last equation using something like loop previously in a loop? I will go F plus lambda multiply by
Here? So at the beginning of the process here, f hat is just 0. Is nothing. Our model is nothing. We're building it gradually. Here I'm just doing a variable update. This is meant to be like Python, right? And these are just bullet points. So our current model at this iteration is the model we had so far, plus lambda times the model we got from this tree. And then we're going to reduce the residual. And as this is a for loop, then we go back up here. B would become 2. It would be the second bootstrap sample. With that second bootstrap sample, we fit a new tree on the new residual. It would be another tree. So here, this one would be, this is at iteration B. This is always some f hat B, right? So this is a collection of small trees that are shrunken and added together. So D in here is called interaction depth. This is interaction depth because, well, if we go with D equal to 1, we're going to only have stumps, and this stump is just based on one variable. Therefore, our model eventually becomes addition of some variables just without any interactions. If D is equal to 2, we're going to possibly have trees like this, and the split here and the split here could be from different variables. Therefore, this tree is capturing some sort of interaction between two variables. Because, for example, this one is some horizontal line, this one is a vertical line. That's why we can create a box, by separating maybe a region like this. This is not linear, this region. Although it is boxy, it involves some x1 and some x2. An interaction of them creates this region. That's why D is the interaction depth. We can either go with D equal to 1, which is just an addition with no interaction between variables, or D equal to 2 is usually a suitable choice. And lambda here is chosen by cross-validation. So, the idea here is that as this is sequential, first we kind of capture, the most important thing, the kind of obvious thing for prediction, and that would be in the first iteration. Then that would be reduced from the residual, and in the next iteration, we attack the residual based on the area we didn't capture in the previous step. That's how we're kind of doing slow learning by attacking the residual sequentially in the areas that gives us the best improvement in terms of our predictions. Does it make sense? Yeah. Capital B is number of bootstrap samples. Yeah, but it's not that sensitive. We usually try something like n. In general, for bootstrap, n is some common choice.
If the capital B is big enough, where the R is 0.
What would be 0? Eventually that would kind of overfitting. Yeah. So the thing is, actually, boosted trees, they may overfit. So this is a disadvantage that boosting has, and random forests and bagging trees, they may not overfit. But with boosting, there is some number of trees, some capital B, that leads to overfit. There was a question. The residual. At the beginning of the process, residual is just a response. Residual for here is just a name. We can call it whatever. At the beginning is the response, is what we want to predict. Then throughout this process, we predict some part of it, and then residual would be what remains to be predicted. Because initially it was Y. At this point, our model is a collection of these things. That's why our predictions are deducted from the response. So residual is, at a point in this process, the residual is response minus prediction. Yeah. Ideally, we want the prediction to match with the response. Yeah. Exactly. In the first iteration. But in the second iteration, the response changes. The response remains to what is left from the response after the predictions we had in the previous iterations. Yeah. That's why this is sequential. So it's a bit unusual compared to the previous one. But eventually, for the performance, For the performance, so this is like performance of decision tree. Let's say boosting in many situations gives us even a more accurate prediction than random forest. But one issue with boosting is that it doesn't stabilize. It may eventually go up. This is one issue with boosted trees. I mean, they may overfit at where B is really large, maybe thousands of trees. So you really need to, make B large for a boosted model to overfit. So it doesn't overfit quickly. That's why lambda is a more important hyperparameter, which defines the speed of learning compared to number of trees, which is kind of about complexity of the model. Because this is number of trees means more complex model. Any questions? Yeah. Oh no, not at all. It's a new tree. It's a new tree. It has nothing to do with the previous tree. It's just a new tree that we fit on X and residual. That's it. Actually, in each iteration, it's a new tree. Yeah. Well, we either go with d equal to 1 or d equal to 2, and this is the maximum number of splits. There could be situations where d is 2, but the tree ends up having just one split. We are not forcing both splits to be used. This is maximum number of potential splits. Yeah. All right, one last thing is variable importance. So from tree-based models, as we had variables and there were like splits based on different variables, we can have a variable importance plot. This is a very basic idea compared to the topic of your assignment, which was machine learning explainability. I think you already learned about many advanced methods for finding importance of a variable, but with tree-based models, we may have, this is feature importance, it's the same thing. So we see how much of the loss function was reduced because of splits on a variable. So this thing shows sum of reduction in loss function based on splits over some xi, right? And then we're going to normalize it so that the variable that gave us maximum sum of reduction in all the trees will be 100. So maybe it turns out that x4 was the most important variable because it was the variable that led to really useful splits. Then maybe the next important variable would be x7. So this is just a plot that we can get from tree-based models, and it tells us what were the variables that allowed us to have splits with large reductions in the loss function, because the idea was reducing RSS or reducing Gini impurity or reducing cross entropy. But from the methods you learned in machine learning explainability, there were also more advanced methods of understanding how variables impact a prediction. So you learned about, well, there were SHAP values, right? There were partial plots, partial dependence plots, right? Where we just change the value of something and see how it impacts the predictions. And there were also, permutation importance. So permutation importance was where we have fit the model, we have the predictions, then we're going to just shuffle one of the columns and see how the predictions would change. That if the column is not important, the permutation would not change the predictions. Partial plots was again something similar, sort of sensitivity analysis. We just take one of the variables and increase its value and make predictions and see whether the predictions are changing when some, let's say, x7 is changing. And then SHAP values, they were the more advanced way of looking at where prediction of a model comes from. So this is kind of about one specific prediction. So this is very useful for justifying a prediction. Let's say you're working you're developing a model for a bank, and your model says this customer, the application of this customer should not be accepted. Well, maybe by law you are required to provide a justification, and SHAP value allows you to provide a justification of maybe this rejection decision comes from the fact that customer's credit score is this value. Let's say their age is this value, their salary is that value, and how these different variables impact the prediction. Any questions? Yeah.
For the importance plot, any variable reach 100% reduction.
This is normalized. So one of them is going to have some maximum value. The maximum value is not a round number. It would be, let's say, 255.6. It's just normal that we divide everything by this, so that this one that gave us this much reduction in loss function is shown as 100. And we measure importance of the other ones relative to importance of x4. This is something that we can get from tree-based models. I guess you're going to see that in your tutorial. Any other questions? All right, thank you very much, and see you next week.